Welcome back. This is still Rosa Badia, and we are heading now the second part of this afternoon session with this panel on artificial intelligence, which will be moderated by Benny Mols. Benny is a Dutch Frisman science journalist, author, and speaker with 25 years of experience who specializes in artificial intelligence and robotics. He holds degrees in physics and philosophy and a PhD in physics. He has written over 700 popular science articles for various national and international media, including the communications of the ACM, and published 13 books, including his most recent one on artificial intelligence, a slimmer, and a pimp, although it's only in Dutch. So welcome, Benny, to moderate this second panel.
So Celeste, yeah. Well, welcome, good afternoon everybody at this panel discussion about learning in machines and in humans. And we are going to look at learning from three different perspectives, from the perspective of computer science, mathematics, and psychology. And I'm very glad to introduce to you three wonderful panelists that we have. And let me start with Dr. Celeste Kidd. She's an associate professor of psychology at the University of California in Berkeley in the USA. And she studies the processes of knowledge acquisition, especially in young children. And she uses a combination of computational and behavioral methods. And to already let you hear how Celeste and the other panelists sound, I'm going to ask all of the panelists one short question and please also a short answer. So to you, I would like to ask, Celeste, you come from the field of psychology. You look at these advances of AI over the last years. You do experiments in your lab with young children. What has surprised you more over the last years, the advancements in AI, or are you still more surprised by the little children in your lab?
I would say they're both surprising in different ways. The ways in which they interact with each other has probably been the most surprising thing. We recently ran a pilot study in consultation with Common Sense Media to see how kids are using things like ChatGPT, and the things that kids come up with to do with it is not what I would have thought. I was like, they're mostly like having it tell them stories that an adult would deem inappropriate and things like this, which is that's a good use of that system that I didn't think of. So, yeah.
All right, thank you, Celeste. Next to Celeste is Professor Po-Shen Loh, and he's a professor of mathematics at Carnegie Mellon University in the USA. And he studies questions that lie at the intersection of combinatorics, probability theory, and computer science. And I have to add, he's also a social entrepreneur in which he combines the mathematics, education, which is really close to his heart, as we will hear, and healthcare. And he has also been for 10 years the national coach of the USA International Mathematical Olympiad team. And Po, I would like to ask you, do you think that AI is already ready to be a member of this team?
Oh, that's a good question. I think the issue is that the current AI might take a little bit too much energy. Yes. However, the interesting thing is that it could become very useful quite soon.
Okay.
I'm sure we'll get to that soon.
All right, thank you. Next to Po-Shen Loh is Professor Brigitte Roede, and she's a professor of biological psychology and neuropsychology at the University of Hamburg here in Germany. And she studies how the human brain develops and adapts through learning processes and how this depends on individual experience, our environment, the way we are brought up. And to you, I would like to ask already, you focus on the wetware, on the neural networks in our brain. I think there are many differences between artificial networks and neural networks in our brain, but can you tell us already one huge difference between these different types of networks?
Yeah, I think the main difference is that human brains evolve in a very systematic manner. And another difference is that human brains age and artificial networks do not.
All right. We will hear more about that later. And finally, we have Dr. Eric Schulz. He's the director of the Institute of Human-Centered Artificial Intelligence at Helmholtz, Munich, also here in Germany. And he's trying to uncover the building blocks of intelligence using a mixture of computational, cognitive, and neuroscientific methods. Eric, you come from psychology, you're now doing a lot of AI. Do you have an example in what aspect of human intelligence large language models like ChatGPT have greatly surprised you in the recent years? So things that we think, this is really a human cognitive capacity, and you thought, wow, a large language model can do that.
For sure. I mean, we run a lot of experiments that are usually designed for people, like cognitive science experiments, on all sorts of large language models, more than 200 in total. And I would say one thing, I mean, we were discussing earlier that I was quite surprised about was recently we tried some studies on metacognition. So how much do you know about uncertainty that you have about tracking certain distributions and so on? And large language models in particular, the most recent ones like GPT-4, they did quite well in this actually, and they did much better than the human subject data that we got our hands on. So that was certainly a very surprising thing that we saw, and we could maybe discuss later.
Thanks a lot, Eric. Before we are going really to discuss about the differences between human and machine learning, I would like to set the stage by showing you two short videos. And the first video will show one of the powers of AI, and the second one is going to show you one of the powers of human intelligence. And I will start with the first one of the powers of AI. We are going back to the year 2016, when there was a Go match played between a supercomputer, AlphaGo, and the best human Go player of, I think, the last couple of decades, the South Korean Lee Sedol. I made a compilation of a couple of fragments from a beautiful documentary called AlphaGo, and we are going to look at the moment that in the second game, the computer does move 37, and we see the reaction of the human Go experts. Then we see the reaction of Lee Sedol, the Go player who comes at the board, and please take a look at his facial expression, it says a lot. And then I will tell something about what this says about the power of AI. Let's take a look.
So, Ajab sees AlphaGo plays the move 37, and Ajab puts the stone in the board.
와, 정말 생각지도 못한.
Value.
That's a very surprising move.
I thought it was a mistake.
When I see this move, for me it's just a big shock. What? Normally human will never play this one because it's bad.
The professional commentators almost unanimously said that not a single human player would have chosen move 37. So I actually had to poke around in AlphaGo to see what AlphaGo thought. And AlphaGo actually agreed with that assessment. AlphaGo said there was a 1 in 10,000 probability that move 37 would have been played by a human player. So it knew that this was an extremely unlikely move. It went beyond its human guide, and it came up with something new and creative and different.
I want to see Lee Sedol when he sees this move.
He's back. Lee is back.
Normally he think about 1-2 minutes, no more. But this time, he think more than 12 minutes. This move is very special because with this move, all the stone played before is work together. It's connect. It looks like a network, link everywhere. It's very special.
I think one of the lessons we can learn from this is that with a lot of data from a very good quality, AI is able to detect patterns that even the best Go experts in many centuries of playing Go had never, ever discovered before. And that shows one of the potentials of artificial intelligence. Well, this was 2016. We are now a couple of years later. I am hoping to see. Can I see the slide with the graph, please? Yeah, that one. All right. So we are now a couple of years later, and here's a graph that has been in the last year quite a lot in the media. And what it shows is the performance of AI systems on human benchmarks. So we see, for example, one of the first ones was image classification, and it shows how much AI has made progress on these benchmarks. Well, some people say, okay, it shows that some of these capacities are above the human baseline. The question is whether that really generalizes, but let's say that for the moment, let's appreciate that AI in many fields has made a lot of progress, even in mathematics. As you can see, there's a news headline telling AI reaches silver medal level at this year's Math Olympiad. All right, so far about power of AI. But there are still many things that humans are better at. And I want to take a look at another short movie to illustrate this.
Oh. Oh. So?
There's no AI system in general which can do what this little 2-year-old kid does. In order to show this behavior, this child, which has never ever seen this situation before, he has to know what the intention of the man is with the papers. He has to know what a cupboard is for. He has to know physically how to open a cupboard. He's even able to communicate non-verbally with the man. This, I often show it in the lectures I give, is an illustration of what is sometimes called common sense. A lot of knowledge, everyday knowledge that we learn from the early age on that nobody explicitly tells us, but that is very important. And in the field of AI, common sense is sometimes called the dark matter of the field, something that we know is there, but we don't know how to put it in our machines. Okay, so I hope that I've illustrated the paradox of AI. The paradox of AI is that what is hard for humans is sometimes very easy for machines, and what is very hard for machines is sometimes really easy for humans. So let's now start our discussion. I would like to start, I first would like to start, I asked all the panelists to come up with a statement. So that's what we are going to do first. I will take the statements of all the panelists, and I would like to start with the statement of a couple of minutes by Celeste Kidd.
So I love that clip that you showed, because it demonstrates one of the most important points I think that we need to make on this panel to open the discussion, which is what does intelligence mean? What type of intelligence do humans have? It's obvious from that clip that there's like a pro-sociality, there's a reading of intentions. We have a paper from a while back that's a theory about why humans are the type of intelligent they are, why we're such extreme outliers. And one possibility is that the reason why we look so different from even our close evolutionary ancestors is because our intelligence may have evolved for the purpose of taking care of our offspring. They have big brains. We are bipedals. They have to be born early, and thus they have to be born with their brains not fully ready to go. They're very helpless. That is very different from a baby giraffe. A baby giraffe is born, and within just a few hours, it can get up and run. If there's a predator, a baby giraffe has a chance of surviving. If there's a predator and there's a baby human on the ground, I was like, that baby human has no chance. So it is likely that the type of intelligence we have evolved for taking care of helpless offspring. We need to be able to read the intentions of a child that is running towards a cliff to know whether or not they might not see it and are going to run off, or whether they're going to take a look. We need to be able to read the intentions of a child that's not yet able to feed themselves, say that they are hungry. This ability may have started there, but it enabled all sorts of other super incredible human abilities, the ability to coordinate and to share information with one another. We are extreme outliers in that sense. And the way in which we do that is largely enabled by being able to read uncertainty off of one another. Humans know what they do not know, and they are signaling that to each other. That child knew that there was something that that person didn't know about how that cabinet opened. They read the intention, they understood that they had knowledge that person didn't, and they volunteered that. That's super different from the architecture of the latest generation of generative AI models. So like those models, there's nothing in that underlying architecture that can even distinguish fact from fiction, much less represent what it does not know. And I think there is potential for things to change. Like Eric, I'm sure we'll have interesting things about metacognitive abilities and where they're going. But for the moment, I think it's very fair to say that the current generation of AI models are really struggling with metacognition, and that's a major limitation.
Thanks a lot, thanks a lot. We will come back later to this curiosity problem, something I would like to hear more about. Next, I would like to have the statement of Eric, please. If you can, in a few minutes, tell your statement.
Keep it short. So I've been working on this stuff now for a while, actually. I was always interested in like what artificial intelligence can do and if we can create a robot that can explain jokes to me and so on. But the first time that I was really surprised by one agent was actually GPT-2, because GPT-2 really, to me, seemed like the first leap, where an agent could do psychology tasks that it couldn't do previously, like hold beliefs, like the false belief tasks and versions of that didn't do so badly on it. I know there were still some weaknesses. Then GPT-3 came along, and we really did some like a battery of psychological tasks, and it really surprised me that it can do some kind of model-based reinforcement learning and these model-based, model-free reinforcement learning tasks. It could do some kind of efficient reward learning and so on, but it back then sucked at causal learning and exploration. And we said, oh, this is probably because it's trained purely passively, and it needs some, like, you just feed in text and it predicts the next token. Probably it needs to learn somewhat more from interactions with people. And then, this is maybe the thing that I want to say is that when we say AI cannot do X, we should probably always put an asterisk and then say, like, yet. Because usually machine learning moves at such a fast pace that when we are pointing something out that an agent cannot yet do, soon they might be able to do this. So RLHF came along, and all of a sudden these agents weren't so badly anymore in causal learning and exploration. In fact, in some sense, they showed more directed, uncertainty-guided exploration than our human subjects. And the same might be true with some of these examples that you have shown. So like the initial AlphaGo basically first starts out with human data, and then you do some self-play where the agent trains on its own. There's some clear rules, so it's like one kind of clearly defined domain. But nowadays, these agents can actually, in this clearly defined domain, learn purely by self-play. So they don't even need the human data anymore because the rules are given, train them from scratch, and I bet they will discover many new moves. In fact, I'm a very active chess player. Like in chess, I think when they started out beating Stockfish, they really changed how professional chess players approach the game. I don't know if there are some other people here who looked into this. And now with these vision language models coming along, where these models are not only trained on text, but also on videos and images, they are actually getting quite good, even at these tasks that we could call common sense. So for example, we did some intuitive physics task on them, like judging the stability of block towers and so on. And these models were quite good at this. In fact, almost as good as our human subjects. And just for fun, because you told me that you will show this video, I gave this video to some of the most recent VLMs and asked what will happen next. And these models can say probably the child or the other person will help this person by opening the wardrobe so that they can put the stuff in. So it's not like they're completely dumb. Yet we still find some issues there, like when you make these agents interact with each other, they oftentimes do know the intentions, at least formally, you can measure this by IPOM-DPs, of the depth of the thought of the other agent. yet they act oftentimes very selfishly, which worries me a little bit. So I think what is missing there is that you might want to make them care a little bit more about us, because you don't know where this might lead otherwise. So yeah, basically every time we say it cannot do stuff, we should maybe say yet, because these agents are going to get scaled up further. Robotics is probably one thing where people work quite a lot right on now. So maybe eventually we can have an agent that sees this thing happening and walks over. I know this is very far away still, but I'm cautiously optimistic.
I think the NVIDIA processors needed quite a bit more energy to solve this problem than this little.
Yeah, actually, one thing is I gave this problem with the, if you have been in the early session, this problem of the raccoons and the mice and so on to ChatGPT, and it came up with some really cool solutions. I don't know where the person is who said this, but like it said, basically you can attach the bait on a string so that the mouse cannot climb up, or you can use a bait that mice don't like but raccoons love, like fish. So it came really up with quite some cool approaches to solve this problem. So yeah.
Before I go to Brigitte, let me show one more slide, because it basically connects what you just said into energy consumption. Can I see the slide with the next one? No, I don't see the next one appearing. I had a little slide with a quote about, there it is, yeah. What I wanted to tell is that the efficiency of the human brain is remarkably good. It's only 20 watt of energy power consumption, which is amazing what we can do with these 20 watt. And I think yesterday, in the talk of Jack Dongara, he was talking about supercomputers using megawatts. So I think that's still an enormous engineering problem. But okay, let me go now to the statement of Brigitte Röder, please.
Statement more from the perspective of brain development, and I will introduce a few keywords which we might later discuss in the panel. So human brain development is characterized by a number of anatomical and functional changes. With a few exceptions, all neurons are generated by the end of the second trimester. But a number of synapses, these are the connections between the neurons, rapidly increase after the infant is born. In the first 1 to 2 years, a large number of exuberant connections are formed. Research in primates, including humans, shows that this process is mostly under genetic control. However, over the following years, the number of connections is dramatically reduced, about half of them, in fact. The pruning process is controlled by experience. At the same time, experience elaborates and strengthens connections that are used and increase the speed of communication through myelination. These processes contribute to the opening and closing of what we call sensitive periods. Sensitive periods are epochs of enhanced neuroplasticity with an increased capacity to learn. Thus, while the brain undergoes anatomical and functional changes, the learning mechanisms available to an individual change as well. Hence, adult plasticity, which allows for adult learning, must differ qualitatively and quantitatively from developmental plasticity and learning. From what I have stated so far, significant differences between human brain development and AI learning become evident. AI is based on artificial networks which do not undergo structural changes. Learning mechanisms are the same throughout the lifespan of an AI system. Another difference is that humans are not passive learners. In fact, humans actively seek out input, while AI is primarily passive in its learning. Humans benefit from genetic predispositions that allow them to profit from the adaptation of prior generations, that is the evolutionary past. Furthermore, humans can transfer knowledge to the next generation using cultural media, which extends learning. Finally, humans possess a high capacity to learn from models and have evolved tools for selecting promising models. The human brain has a limited capacity, approximately 80 billion of neurons. Communication between neurons involves biochemical processes and therefore is rather slow. In this respect, AI is largely superior. AI's storing and searching capacities increase with rapid technical advances and the amount of available data. The human brain mitigates this challenge through abstractions and generalization. In fact, the limiting working memory capacity in infants and children compels the brain to formulate rules and generate principles applicable to countless instances. Given these examples of differences between humans and AI, I would like to raise the question of whether it might be better to adapt AI learning to the given technical opportunities rather than predominantly to human brain development and learning. On the other hand side, we must consider how far AI can improve given the limited food available for it to learn. Thus, if no new breakthroughs are expected due to the lack of additional teaching material, we might need to reconsider how we can change AI to generate genuine new knowledge like humans do. And thus, I think we are back to human brain development and learning.
Thanks a lot, Brigitte. Last but not least, Po Shenlo, please.
We're in trouble. We're in trouble. We're in big trouble. This is my opening statement. We're in big trouble. I want to say my angle on all of this comes from, I'm actually a math PhD. I studied pure mathematics. I studied combinatorics. I even did research in combinatorics. Then I got distracted by the real world. And now I actually work all the way across as a social entrepreneur. I work in business. We actually even have real people that we work with, and this gives us a direct feedback loop to real people. But because of that, because I actually also do this real direct work, that's why I'm a little bit tired right now, because I was up until 4 a.m. working with my buddy Claude. You know, there's this company called Anthropic. They make an AI called Claude. If you're trying to make real software to go into servers, Claude is pretty darn good. I say this because I'm not trained on that at all. I'm a professional combinatorialist. But today, actually, if you have a very strong background on math, problem solving, general technical things, man, I can ask this thing, please help me deploy to Amazon Web Services. I'd like to have a memory cache. I'd like to have a database. I'd like all this. You'll give me all the code I need to do it, and it won't be completely right. But that's okay, because actually, when you're trying to solve a problem, sometimes one of the most powerful things is to know that there exists this tool. There exists that tool. In some sense, the value of an expert is that the expert knows that various things exist. Sorry, I'm a mathematician, that's why I have to use that word. But if you know that certain things exist, suddenly it saves you so much time. So even though I might have to do a little bit of fine-tuning to go and make sure it's absolutely correct, my gosh, it saved me so much time with there exists. I told you I'm a social entrepreneur. I run the business. This has fundamentally changed the way I hire software engineers. I will no longer hire a software engineer who just knows how to make stuff. In fact, at this point, if you want to be a software engineer, you need to be very, very good at critical thinking and very, very good at learning. This fundamentally changes that job market. The big kicker, though, is that it's cheap. Actually, the biggest thing that scares me is that the GPT-01 got released just very shortly ago. That can solve math problems, math competition problems, actually better than I can. Now, I commented about energy earlier. The International Math Olympiad AI, that was an intense amount of compute. But because, again, I have the business side, I went to see how much would it cost for me to use GPT-01. Actually, if I want to use it, I only have to pay $15 for every 1 million words that I send it. And it can solve crazy hard math problems. If you know, math problems don't have that many words in them. So this is an insanely good deal. I think most people didn't connect the dots between International Math Olympiad AI costs a fortune to run, But this other one, which is already better than most human beings in problem solving, costs almost nothing. This is going to change the whole job market. And when I look at this, this is why I say we have to do something as a society. In some sense, when we think about what will AI be able to do, what will humans be able to do, if you ask a mathematician to say something, I won't say AI won't be able to go somewhere unless I can prove it, right? And then I thought a little bit, how did this evolve? What is this optimized for? This is not optimized for compute. This is optimized for reproduction. Reproduction, okay? And now we're competing against things which are optimized for compute. So ultimately, we have a lot of societal questions. I'm happy to talk about all of these things, but ultimately, we need to do something to help increase the human capability, increase the human cohesion. This is how I see it.
Thank you, Paul Shanlo. Okay, let's dive a bit deeper into this subject of learning, differences between machines and humans. And I also want to discuss later on the impact of AI on education, something which you can all tell something about. Let me start with asking Celeste. You were telling about the importance for human beings of knowing what you don't know. Yes. Can you tell a bit more about that?
Yes, I would be happy to. So I talked about that one of the things that this enables is coordination, collaboration, sharing information. Another primary function of knowing what we do not know is that serves to help direct us towards discovering new information, asking questions. Our curiosity is driven by specifically our representation of what we do not know. I was like, we are attracted to resolving uncertainty that we recognize that we have. One of the things that I think is most beautiful about people as an animal and as a species is that we're so diverse in terms of what we are curious about. And that's coming from the fact that each of us has a very different set of existing experiences in the world. Depending upon what you've experienced, that determines what you currently believe to be true. What you believe to be true determines what you are interested in sampling next. And so without that representation of uncertainty, without knowing what we don't know, we cannot be curious. And one of the things my lab has been working on recently is I started to write a book, and I started to write that this was a universal feature of biological intelligence, and then I realized we've actually only run like macaques and human infants, and that's not a very large sample of animals to be claiming universal. So we're currently in the process of running parrots and dogs and basically anybody that had animals that they would let us borrow for a minute, so we can do these psychology experiments we're doing right now. And I now think that as like soon I will feel more confident in saying this is a universal property of biological intelligence. There's definitely like a lot of evidence suggestive of this. I don't think that kind of metacognition, that type of representation exists in AI systems that I have seen. I like your asterisk point, but like there's some cases where you can say like, this won't lead to this. Like I'm not going to be able to make ice cream from a stone ever. I don't need an asterisk to say like yet. There's not enough stuff in a stone to get me ice cream. I don't think you can have curiosity of the type that biological intelligence has using the components that we are using to construct current AI models. And until that changes, I don't think you need an asterisk to say they're not capable of the same sort of richness in self-driven learning, curiosity, also innovation. So like coming up with the idea, humans don't just play Go and play chess. We came up with the idea of games, and then the specific ones, Go and chess. No generative AI model that I know is very good at generating games. Like it will do that. If you give it the instruction, it'll generate a game, and if you play it, you might find is not very fun. That's not the AI's fault, as like it doesn't have all the multimodal experiences. So I think that component being missing from current AI models is something that we have to solve. I'm super interested in what everybody else has to say about this.
If I'm correct, Eric, you are working on trying to get curiosity in AI systems.
Maybe just very quickly, sorry for always being the potty pooper about these LLM criticisms, but like, so whether or not LLMs have a critical period when training, it's an open question that people are working on. Ryan Cottrell and some people at ETH have a paper where they claim that they might. Whether or not there are different circuits in the LLMs is also an open question. There's a whole field called mechanistic interpretability that is working on this. So you should be cautious to say that they might not, because they might. We don't know yet. Then the curiosity, so because that was one of the first things that psychologists shot back at machine learning researchers, that these models cannot gather information to solve certain tasks, like find out what is important. Several people, including big companies, have worked on this, and it has improved quite a bit. If people remember using GPT-3, it would never ask you a question back. But the latest models like GPT-4o and so on, they do ask clarification questions. And then when you come to curiosity, I have seen this many times that psychologists tell me, oh, but it's not curious like this. But then once you have a formal definition of curiosity that you can test experimentally, then you can run this on LLMs. And then what we often do see is that they do show some of these forms of curiosity, at least in these tasks that psychologists have come up with. Of course, there are still cases, I'm not claiming that they can do everything yet, where they might fall short. So I'd be happy to discuss that, because that could be something where you can train on. One thing that they used to do is, with RLHF, it was basically just optimizing whether or not you finally liked the thing that you got, like thumbs up or thumbs down. And people are now changing that reward function when you do RLHF to do other things. For example, how much more likely is this person to re-engage in a conversation? Right? You don't only want to like what I say. If I was just optimizing that, I wouldn't go against what people have said. I might want to optimize for, like, what is the probability that we will talk again or something? Or what is the probability that you think you'll learn something from this engagement? And people are actively working on this. It's a big community of research.
Do you have a practical example of why we would need an AI system which is curious?
Yeah, so I mean, one classic example in reinforcement learning is in the multi-step case. If I tell you, I would love to eat ice cream right now, right, then the GPT-3 would have just told you, like, oh, blah, 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 vanilla ice cream is a very popular ice cream, whatever. Nowadays, these systems start asking you questions. So it's like, where do you currently... And then I have to say Heidelberg, oh, and what kind of taste do you like with ice cream and so on? And then it tries to build a model of you, and then it tries to recommend to you an ice cream shop nearby that might have the ice cream that you actually like and is open right now. So I would say that this is a form of question asking based on uncertainty that you have about the agent.
I saw, Brigitte, that you would like to react.
Curiosity is extremely important in order to detect something what you can't predict. So you have to detect the world from which you can learn. So that's what I meant with active learning. So children seek for information because they're curious, and passive learning is just receiving what it is experiencing. So this is, I think, important why you need curiosity. To sensitive periods, so I'm aware of the data that deep learning networks show something which looks like sensitive periods, but in contrast to human learning, you can revise. So you can change the complete system because the structure of the networks or the artificial network does not change. But in humans, all the synapses are pruned. And some of the myelin causes, the generation of myelin causes, the system can't change anymore. And it causes a hierarchical network, and the hierarchical network allows for abstraction, etc., what we discussed before. So therefore, just showing that something depends on prior learning is not equivalent to sensitive periods.
Yeah, I mean, I'm just saying that it is an ongoing question, right? It's the same with networks. Like, we do find networks in LLMs like Llama. Actually, Meta has done us a huge favor with releasing these weights, because now we can do some neuroscience on these models, which we did, and we do find some networks that track things like prediction errors, and they evolve as the model is trained and so on. And people are they are trying to find things like sorting algorithms. What kind of sorting algorithms might you be able to trace in these algorithms and so on? So all I'm saying is we should be cautious. It's an ongoing debate.
Yeah.
But of course, there's no like biological chemicals in the architecture.
Let me go from curiosity for a moment to AI in math. And I would like to ask Po, do we know what AI is really good at in solving these math problems and what it is not good at? Or are we still discovering this? Can you comment on these performance of AI in all these math questions?
Sure. I think that it's always right now it's early days. Because I will say, I was at the International Math Olympiad this year. I saw the problems. We actually knew that there were AI companies trying to do the International Math Olympiad problems. And I'm in several group chats where after the exam, we were all talking in the group chat saying, man, this exam was basically as hard as you could make it for the AI. There's no way it's going to get anything. There was only one geometry problem, and it was the easy one. It was question 4. If you know the layout of the International Math Olympiad, they put it in the easy position. So because it was already well known that AI could solve geometry problems. And the rest of the questions looked weird. Actually, I'm in a group chat which has a former United States national team. I won't say which year, but they were a #1 ranked year. That year, the US won. And in that group chat, people were chatting about how, yeah, it looks like this is going to be really hard this year. 10 days later, OpenAI managed to get 4 out of the 6 questions. Somebody replied to one of those comments in that group chat and said, lol, that didn't age well. Meaning, we completely missed it. So what I'm trying to say is, there are a lot of us who were surprised, but then what we said is, okay, at least it ate a ton of energy.
Yeah.
Right? Because that's like, okay, at least they took a lot of energy to do that. The thing that's surprising me is the new O1. And why I'm mentioning this is because a lot of media, a lot of times when people report on this, they say, oh, AI did some problems, AI did some problems. But one of the interesting things is now AI can do some pretty hard problems for really cheap. See, look, the way I'm talking about all of this is I'm sorry, I don't have the oh, sorry?
When you say cheap, I was like, are you talking about the cost that you're running for like words in the query versus the computational costs? Because those are 2 different things, right?
I think the way I look at it is that it's economics. And so if it costs them as much as it costs to run the AI for the IMO, they would just go bankrupt. Because I can send queries. I myself have been sending queries. I did it last night to help me with my software engineering. So I was actually sending queries into that model for the super cheap price and getting very high quality output.
Right, but I don't think the cost that you're paying is the amount of compute that's being used. And I think right now that we don't have that, there's no transparency on that. So sometimes a cost, what I am paying money-wise is not how much it costs in terms of water to cool the machines that are running these things or train the models. Right. And I think it's important to keep those distinctions.
Yes, I agree. Right? But the point is they're not bankrupt yet. And what I'm trying to say is that if the order of magnitude was the same, they would be bankrupt very soon. Mm-hmm. Because what I'm explaining is that it actually costs money to run those servers, right? And the volume of queries that's going into O1 at this point is large enough that if the order of magnitude of energy cost that they're using is the same as the International Math Olympiad, they'd be bankrupt. So what I'm explaining is that I look at everything actually from the point of view of economics. Because ultimately when we think of society, there are jobs, people, we all exist, we have some role in the society. And so today, yeah, I agree with you, by the way, a lot of these companies run at a loss. Yeah. However, you can't afford in business to take that big of a discount. Right. Yeah.
Yeah, I think it's important to consider, though, not just the financial aspects. So, there's lots of stories. Sherry Wong has some really good work communicating this about money being rerouted from vulnerable populations to cool machines. So those are costs that may not come out in the numbers. I was I'm not an economist, but those are costs. Those are pretty serious costs. So yeah.
I totally agree. To me, those are indeed real costs. But the thing I was talking about when you compare apples to apples, you're comparing the GPT compute costs for the O1 and then the thing that they were doing on the other side. Both will incur the same type of ratio costs on those populations. But I totally agree with you. Actually, that's why I see all of this as issues. Yeah.
Yesterday, Alexei Afros gave a beautiful lecture about the power of data and that we need even more data. But on the other hand, we also know that humans can learn from very few data. I think, how long does it take for the average person to get a driving license? Maybe 40 hours or so. And self-driving cars have been under development for decades with I don't know how much data. So I would like to focus a bit on this data versus models. Celeste, how do you look at this? Data versus needing a lot of data to feed in all this AI models versus humans who seem to kind of generalize more easily with much less data.
Right. So this is an unconventional answer. You see a lot of comparisons. Gary Marcus sometimes talks about the models being data hungry while children can learn from one instance of, for example, seeing an apple, hearing an apple. An open question, I think, is that the types of data that people have versus the models have are just fundamentally very, very different types of data. A child's single experience with an apple is not one picture of an apple on Google Photos labeled apple. I was like, a child's experience with an apple is like sensory. They're feeling the apple, they're seeing the apple, it's multidimensional. I was like, there's tactile components, there's social components, somebody labeling the apple, there's the taste components. The data that people are getting is much, much richer. And there are tons of correlations you can pick up on in order to leverage things like learning and generalization. You mentioned the limitations of the human brain, and we've also talked a little bit about like how costly compute-wise these models are. I think it's an open question as to whether a model could become more efficient at learning if it had the same sorts of rich correlational multimodal data that people have. So I think that'll be a thing that comes up in the next few years. It's something that's very important to sort out. I think it's an open question. We don't know.
Yeah, Brigitte, how do you look at this problem?
Yeah, so I mentioned that we have a brain which is not naive. So we have a lot of knowledge already in our brains when we are born. And we can build on these predispositions with a few data which confirms and shapes these brain structures and the knowledge in our brain. So multimodal data you mentioned. So we know already prior to having this experience, some of the relations between the inputs through our ears or via our eyes or our touch. So I think these strong predispositions and brain structure which we have in our brain, and then the capacity to select from an overproduction of connections allows us to shape our brain with fewer data than compared to an AI system.
Do you see ways how AI can learn from observing the human brain, what's going on in the mind? Can AI learn from your field to maybe use less data?
So I mentioned that we learn from our evolutionary past, but AI models could be simulating evolution, right? So that would facilitate the new generations of the AI system to quicker learn from fewer examples if the experience, so the knowledge acquired in prior generations could be used.
Yeah. Eric, can you comment on that?
So, I mean, these questions with the timescale of learning, and so, I mean, first preamble is these models' carbon footprint is worrisome, and this is something that should be reduced. Many labs, including mine, work on this, but it is an open issue, of course. But then the comparison to humans is a bit complicated now, because if you consider this kind of like data and episodes as pre-training, then the question is, what would count as pre-training for a human, right? It feels a bit selfish to say these models take so much energy while we're literally havocing the whole planet to get to the point where we currently are, right? And we have evolution and so on. So these timescale comparisons are a bit tricky to make. Maybe there is some kind of culture, like people have claimed that there's some kind of cultural evolution going on, even on AI architectures, right? In some sense, nowadays, almost everyone is using transformers. Maybe something else will come about, but this could be something that is changing. So I think it's difficult to say like so much from so little.
Yeah.
Also, having now a small child on my own, I don't really believe this so much from so little anymore, because you have to give a lot for these guys to learn.
Let me focus for a moment on the problem of bias. We know that I think cognitive psychologists have a list of 150 different types of cognitive biases that we humans have. On the other hand, we know that AI systems can be very, very biased. How should we deal with these biases? Can we combine the two intelligences to get less bias in the combined system? Or how do you look at this problem of bias?
Yeah, so the issue of bias is multifaceted. In the context of generative AI models, we know there's a ton of work at this point showing that the rate of fabrication, so like things that they say that are not true or not consistent with world knowledge, is very high. these models are full of negative stereotyped biases, both gender and racial. When you have those systems interacting with people, one of the things that I think we need to be very cautious about, there's not enough attention on, is the very, very real risk of the biases in these models being transmitted to human users, potentially in perpetuity because of the nature of model outputs. Because these models currently, their existing architecture, these transformer models, do not have the ability to know what they don't know. Their outputs are confident. They're unlike human outputs in that way. When we don't know something, if you ask somebody for directions, if they don't know the way, then there'll be a delay before they give you the directions. You might hear and they're not doing this consciously, but unconsciously, people pick up on this and they're able to moderate the degree to which you adopt somebody else's beliefs based on your estimate of how sure they are. These models confidently spout racism and misogyny. And when you have those systems interacting with people who are, we know from our research, using the same cues in order to assess it, you run a very serious risk of a person going to a model at a point at which they are in a magical state where they don't know, they're looking for information. That's the point at which they're open to changing their minds. They enter the model with their query in this state, and if they get a very confident answer back, the risk is that they move from being not sure, being open to changing their mind, to being very sure very quickly. And once they've hit that state, they don't revisit it. So the biases in these models, I don't think anybody at this point is denying that they are there. But I hear a lot of talk about, well, we'll address them, we'll get better. I was like, this will be an iterative process. Once you have these systems interacting with people, it's a problem, and you may not be able to take that back. And I especially worry about these systems being used for populations that are not represented in the training data. Like I've heard a lot of talk about these models being used for giving educational opportunities to kids in refugee camps. I can't think of a worse application for these models than that. You run a real risk of providing information with serious consequences that's not right to kids in need. So.
But on the other hand, there was, I think yesterday, a question from a young researcher who said that her black face was not recognized by a human immigration officer. He couldn't see whether she was the same person as in her passport. So this is a human bias. So I would think this is something maybe you can correct it with using an AI system.
There's the promise of doing that, and I think in some cases that's applicable, but I bet that this crowd has all seen Joy Buolamwini's work and the Netflix documentary about like what happened when she was trying to use the system for an art project, and it just doesn't recognize black faces. These systems are often pushed and sold on the promise that it can eliminate human biases, but it is hard to anticipate the ways in which that will not work out, and they are sometimes implemented with very real consequences for things as serious as sentencing guidelines, immigration, financial decisions. So, this is not a trivial issue or something we should worry about later, I think. You can't be reactive.
We have about 15 minutes left, and I think I would like to spend 10 minutes on the impact of AI on education and use the last 5 minutes for a short Q&A with the audience. Let me go to the subject of the impact of AI on education. Po, you are very into education, you really care about math education. What is your feeling? What's happening with AI in math education? Maybe also computer science, if you could comment on that. What will be the impact?
Sure, this is indeed what I work on. So very happy to talk about it. So first of all, I totally agree with the statement you said about how giving AI-powered education to people who are vulnerable, this is not, I totally agree with you. This is a terrible idea. Now, of course, there's something else I brought up too, which is what kind of education do we need? In some sense, because there are now tools that can give you this exists, that exists, everyone needs to learn a critical skill called how do I solve a problem if I have no idea what to do, if I've never seen it before. And this is a fundamental new thing that needs to be taught in education. Unfortunately, a lot of people go through school where they are shown how to do it, then they practice it, and then when the exam comes, they are supposed to remember it. That's a good task for AI, right? So we need to mass educate. So actually, I can tell you what I'm doing, because I actually work on this all the time. See, in order to find enough people to coach all of these, we often teach middle school kids. In order to teach these middle school kids how to be able to think of new ideas, you need lots of coaches. And I use game theory and economics to try to figure this out. I realized there's lots of high school students all around the world who are actually really clever. And you know what would help them? It turns out that it's really useful to also build communication skills, if you combine both IQ and EQ. So I started a program. We find high school students from all over the world who are really clever at mathematics and kind. And then I hire professional comedians and actors to teach them how to be charismatic. And not just charismatic, how to listen to people, how to understand, to make that emotional connection so that we can have whole people. And if you want to learn that skill, you also need to practice somehow, right? So you have to open your mouth and say something. What is the easiest thing for math people to talk about? Math, or yeah, what they're interested in themselves are math, right. So actually that solves the scale problem. And then we're then able to scale out teaching problem solving. Actually, if it's possible for the background people to put on the video with no sound, I can tell you what we did is we actually managed to even do this in a way where we made the math lessons look like Twitch gaming streams. So this is an example, just hit the play, but with no sound. This is an example of two high school students teaching together, and what's happening is while they're teaching, we pay for a professional actor to be in that Zoom classroom as well, watching the high school students, giving them real-time feedback to help improve the way that they communicate. So one of the other ulterior motives I have is to try to make it so that someday scientists and mathematicians might even have greater influence in the society. Thank you.
Yeah. May I say something?
Yeah.
Artificial intelligence has, these networks have a lot of knowledge, and what I learned is that the amount of knowledge which is currently available is enormous compared to, say, an years back. So I think for teaching, it's crucial that you teach where you can get the knowledge if you need it, because we can't store all that knowledge. So I think this is, for education, it's important to teach students, pupils to know how to use the system, AI systems, to get the knowledge at a point when they need this knowledge, because the half time of knowledge is also decreasing. On the other hand side, if you want to become an expert in a certain field and you want to solve creative problems, so creativity hardly or crucially depends on having a lot of knowledge in a certain field. For that field, you need to acquire the knowledge you own. So I just wanted to say, so you can use AI for certain problems, but not for all the tasks.
Eric, what is your take on the impact of AI on education?
So I mean, obviously it has the capability to transform education by quite a bit. I guess everyone agrees on that. Like, I mean, I don't know if you use ChatGPT or Claude. I'm using ChatGPT every day, and it has changed my life a lot, because now I have, like, in my pocket basically someone I can ask the craziest questions that come to my mind, and it instantly responds. And this iterative process of knowledge construction that I can have with this agent, even if the agent sometimes goes off the rails, I quite enjoy. And it really has changed how I interact with information and so on. Or you can ask it to create the quiz about Heidelberg while you're going through Heidelberg, show it pictures, and it will ask you something or tell you something new about it. And that's quite cool. One thing that I still sometimes think is, in terms of how we train these models, if we're really optimizing for how much basically we like what the model says, these models become very agreeable with us. And that I sometimes don't enjoy so much. I wish there could be a knob that I could turn to make the model sometimes a bit less agreeable with me. Because true knowledge for me comes with like for example, my lab, when people disagree with me and they tell me something new. But if, these models, I can tell them anything and they will agree with me most of the time. Unless I give pretty outrageously wrong claims, they always are kind of like sycophants or so. Like they really like, and there's research on this, that RLHF makes this tendency worse. So I think this process of disagreeing with someone to really create new knowledge is something that could be, if there's lots of intelligent people here, someone wants a research topic, I think that could be a really interesting topic to work on. As well as I think Celeste will probably say something about optimal pedagogy or so on, right? You have to have a model of what is the knowledge gap in the other person, how can I best close this by providing something that they do not yet know, but then I also have to deliver it in a way that this other agent actually doesn't get upset at me because I'm patronizing or I'm like basically talking over them. So I think there's lots of applications where these models have to learn to interact with other agents in like a better, more dynamic and also more variable way. And that's a good research topic to work on right now.
Would you like to comment on it?
Yeah, so you mentioned reinforcement learning with human feedback, making it more agreeable. It also increases likely increases the rate of problematic negative stereotype biases because of the way that process happens. You mentioned also like enjoying it even when it goes off the rails. But I think something super important to appreciate is you're an adult that's had a lot of experience with the world where kids are not able to detect when it's gone off the rails. Not just that, but people are interacting with large-scale language model outputs without realizing that's what it is. So it's like when it appears at the top of your Google search, you don't realize that it's there. I don't think that these systems right now are well suited for teaching kids about the world for most things, with possibly the exception of programming. I'm an advisor for Common Sense Media, which is an organization that just had a report that came out 2 or 3 days ago using on data of what kids know about AI, what they understand, how they use it. And the summary is that kids in the United States are using it much earlier than we had realized, starting at around age 8. They're using it at rates that are much higher than their parents and their instructors had realized. Once a child had used it for an assignment, which is the primary use by the time they're teens, once a child has done that, for a homework assignment, it's now replacing basic search for them, meaning they are going to these systems in order to find out what's true. And they won't know when it's gone off the rails. These confident answers run a real risk of depleting natural curiosity in kids by being a sort of end of the road. They give a complete answer and don't allow kids to continue to learn. So yeah, I could say more about that, but I know we're low on time. So instead, I'll say that report exists if somebody wants to check it out.
Thank you, Celeste. Before I start the Q&A, I would give the last word to Po to comment.
Yeah, this is nice. I actually just wanted to give a tip to all the young people, because in some sense, we've been talking about using this AI. And I'll give the same tip that I just gave to my 18-year-old daughter. She's starting college now. And I told her, what you should do is you should go and learn in your classes, but you should make sure you don't take too many classes so that you can have time to go and watch the seminars. You should go to the seminars and start noticing which keywords keep appearing, and then go home and ask Claude and OpenAI and whatnot to start giving you pointers. Don't believe everything it says, but use that to start stitching things together, right? And this is, of course, learning math, learning computer science, not about learning other things. But if you're learning math or computer science, which might be a lot of the audience in this room, right? If you're learning these two, and if you're still growing up in your careers, it's actually super useful to go to the research seminars to see what actual people are doing. And in the old days, when I was doing this, I wouldn't have a good way of tracing to figure out what in the world's going on. But today, you can get a breadcrumbs of clues. So that's the advice.
Thank you, Paul. Now I would like to start a short Q&A for about 5 minutes. Please introduce yourself briefly and keep the question short and to the point. I will go from the front to the back of the room, otherwise the people in the back will not have a chance, so please.
Yeah, hello, my name is Matthias, I'm an alumni here. So my question is, I'm sort of interested sort of across the panel, based on your experience with these sorts of AI models, what is currently the simplest thing that LLMs are not able to do?
What is the simplest thing that LLMs are not able to do?
What's your intuition about that?
Yeah.
Okay, so my information might be out of date, but my understanding is that the reason why the LLMs can do arithmetic now is because they feed it into Python. But if you actually ask them to straight up do the arithmetic, I believe it's designed to not always say the correct, it's not always supposed to say the highest probability thing. So here's a mathematical statement. If it just does a long enough computation, it would be like just like me. I'll make a mistake at some point.
But if you give a math question to ChatGPT or another LLM, do you have a sense of when it's going to answer the question correctly or when it's going to make a huge mistake?
So again, for me, that's one of these things where if it's doing a lot of tasks, the error probability builds up. And so whenever it's giving me a long chain, except the O1 has a little bit more error correction now. But generally speaking, the longer the chain, the more likely it is that something goes off the rails.
You wanted to comment?
Yeah, I just wanted to say something because you said the simplest thing what an AI model can't do. Simple means from your perspective because it's simple or easy for you. But it does not mean that it's easy for the brain. The brain might have evolved a sophisticated machine in order to solve that problem. So it is in fact a very complex problem which the AI can't solve. So I think what is difficult is always defined by the ease we feel about it, but it's not based on the computations the brain has to provide.
Yeah, Eric?
There's actually 3 very easy things you can go and try yourself. Like one is the first thing that people try in math is these like multiplications of several-digit numbers. So even like there are the latest models, once it's like 6 or 7 now digits, they are still doing mistakes. That is one, it's very easy and they still sometimes do it wrong. Then anything to do with tokenizations. So tokenization is a really, really black magic. And there are like these funny examples, just Google it, like where if you give the wrong token, it like gives you something crazy because there's this one Reddit user who has that token. So like that is one. But then one that I find fun to do is like do something like, let's play a game and pretend that Zurich is the capital of Germany. And then like it says, okay, now we will play this game. Usually now it takes you 2 to 3 questions to ask and it will not be able to hold this belief consistently and fool you. That's always quite disappointing that it can't do yet. Yeah.
I will take a question somewhere from the middle of the room. The lady over there. Yeah. Can you throw it behind or I should bring it there? Oh, so yeah, I can't take all the questions. So I'm sorry. Yeah.
Okay, so I've been a math teacher for 6 years, and I've learned a lot from good math teachers in general, and bad math teachers. And I realized that something very important about being a good teacher is empathy, and being able to read the student, the body language, to relate, to change your tone based on that. So my first question is research done in the field of AI teachers focused on trying to give these agents the ability to have empathy for the students? And then my second question is, if we do reach a point where these agents have this ability and can actually be good teachers, what do you think of a world where all human teachers are replaced by AI teachers?
I'd love to hit this one. So first of all, I totally agree with your statement, which is why for all of our people who are teaching, the first thing we do is we teach them improvisational comedy. Okay, and if you haven't taken those classes before, I strongly recommend it for everyone in this room. But now the thing about this is, if you're using the AI to teach people, I'm going to give an even deeper reason why I think that's a bad idea. If you've made the AI so empathetic that kid says, man, interacting with this AI is more fun than talking to people. The easiest way for robots to take over the world is for everyone to fall in love with virtual fake things that don't exist. Just wait 100 years. I'm not a biologist, but I promise you there'll be no more people.
Thanks a lot. Thanks a lot. We are running out of time, so for my part, I would like to close this wonderful panel session with a quote from actually a Turing Award winner from 1997, Douglas Engelbart, a pioneer in human-computer interaction. And he said, and I quote, "Technology should not aim to replace humans, rather amplify human capabilities." And let me add that I think the same is true for AI. We can also view it as augmented intelligence. I would like to thank all the panelists. Please give them a round of applause. thank you all for coming and have a very good evening and a good dinner. And the last word is for Rosa.
Thank you, Benny. Thank you, Benny, and all panelists for this so interesting panel today.